So for the last part of today's lecture, I want to actually start with some of the topics, namely mass spring systems. As mentioned before, this is going to be the first physical model that we look at, kind of move from the particle viewpoint towards a more volumetric modeling of a material. And it's also a good one to actually explore some of the fundamental topics of simulations, namely integration methods, which sound abstract, but we'll get to why they're so important and central for many simulators later on. Right. So let's start with masses and springs, and of course what's important to note here is this is not only about what you see here on the screen. This is a classic metal coil spring. Mass spring systems are actually a surprisingly general formulation. In something like Hooke's law, you can actually use it to model electric circuits, for example. With coils and capacitors have also a spring-like behavior, and in this lecture we'll also target very flexible settings. So later on with these mass spring simulators, potentially you could use it to do a variety of things. One example shown earlier is is cloth, like material like my shirt here. Difficult to see, but right, this piece of cloth is something you could model with a planar mass spring system. Typically, when we think of cloth, it's actually fairly inextensible. It's not so much the elasticity here, which already is not so easy to simulate. Then actual volumetric objects like tissue of persons could be something to simulate. I don't have a good example right now, but the easiest case here for elastic objects would be something like a rubber object. A rubber duck would be a classic object to simulate. Or here actually on the screen you can see this, the grimace of this character in the center here. In this case also the face was actually modeled as a mass spring system. Looks a bit scary here, but it's one way to actually deal with the different forming parts. Or also the screenshot here in the bottom is a good example of a medical simulation. So in this part, our organs can be modeled as volumetric elastic objects with certain behaviors, and this is actually relatively widely used in medical simulators, although the more advanced ones use some more complex material models. Yeah, so how do we get there? For that we kind of need to start with the classic particle system viewpoint, and this is something you've seen from, for example, the game engine design class potentially. So here we had these projectiles, and this is now a relatively simple setup. We have particles that start out with a certain position, x of t, moving with a velocity v of t, and experiencing an acceleration. And all of these three quantities are now functions over time. They potentially change. When we're in 2D, these would be two-dimensional vectors. In 3D, they would have three components. But this is now basically these three functions what we need to track over time in order to describe and compute the motion of such a projectile. And now these of course go together. They have important relationships, namely that we could start with a position and compute the velocity from it. Traditionally, doing that would actually require a derivative. Our functions, the position function has a parameter time, so if we take the time derivative of the position, that actually would give us the the velocity, right, the change of position over time, that is the velocity. And we can, of course, also mathematically go the other way. If we have the velocity and we want to compute the position, well, then in order to kind of invert the derivative, we can integrate. So the velocity basically are the changes, and if we accumulate the changes, we integrate them, then we can actually recover the position information. Yeah, these are the relationships. Actually, acceleration, likewise, is actually the change of velocity. It's a derivative of the velocity. And the crucial law now that comes into play here to compute the acceleration in practice is Newton's second law, as mentioned before, right? This is one of the foundations of all of modern day physics, and Newton's second law is one that I'm sure you're all familiar with, and this will come back probably almost every single lecture over the course of the next few weeks. I mean, in a way, it's simple enough. Right, we have F equal to mass times acceleration. The force is computed by mass and acceleration, and from that, often we actually have a force, know the mass, can bring mass to the other side and compute the acceleration that a body experiences. One good example is gravity. We're in a two-dimensional setting, indicated here by the transpose on the side. We would have, assuming we have a y-axis that goes up, we have gravity minus m times g acting downwards in a negative direction, g being was constant, 9.81 and so on. Yeah, so now what do we do with it? We have these two basic relationships. We know the velocity is the derivative of the position, and same holds for acceleration for the velocity. And now in this specific case, we can actually put that together directly. We can actually insert the two updates here. So basically, if we say the acceleration that you see here at the top, this is given by Earth gravity. Notice from before we actually had quickly write that out here. We had a force, it's basically minus m times g, and then we know the force is equal to mass times acceleration, so this is mass times acceleration. If we now multiply both of this 1 over mass, then the mass drops out here, and we are left with an acceleration of minus g. Hence, irrespective of the mass of a body, it experiences the same acceleration in gravity, which we all know from nature around here. So this gives us the first relationship. So the velocity changes, right? The acceleration is the change of velocity, hence minus g over time is the change of the velocity. And then we have another relationship. The change of position is the velocity over time. And if we insert both of that and put it together, then we get this equation here. So we have a factor of t for the initial velocity and a factor of t squared, due to applying this twice, for the acceleration. And in this case, nice enough, we have an analytic solution. So this is in a way the simplest possible case, and something that later on will not work anymore. But now we have a closed form solution. So here I can evaluate the position of my projectile at any point in time from scratch. So this is typically only possible for very simple functions, and for all practical mass spring systems, even with pretty few springs later on, this will not be possible anymore. But the neat thing about this function now is if I undo these parts, that if we start out at a certain position, x0, and we're given a certain velocity v0, then over time, with this, I can compute the motion of my projectile at any given point in time. I can first do that at t equal to 10 if I want, and then later on I can query at t equal to 5 or so. I can arbitrarily, I can arbitrarily jump around here and just go to 1,000,000 or 1, right? I can query this analytic solution at any point in time, which is neat, but again, later on typically not possible. What we'll need later on in terms of integration methods is actually to move forward one step at a time and build the solution over time. We cannot just jump to any later state, but we need to earn it. We need to work towards that state in the end. But for these simple settings, nicely enough, we can actually do it. And this is actually now here with a squared gravitational acceleration and the dependence on the initial velocity. This is a very basic and fundamental solution, giving these parabolic curves that I'm sure you've all seen. So this is a good starting point. Now one kind of one central challenge that we'll have later on is that the acceleration and or the function for velocity might be really complicated. Typically what we'll be having actually from the mass spring systems is we have internal forces giving us accelerations applied by the name forces, and these will be very complicated functions, not like our minus n times g, but something potentially depending on many neighbors in the material. And then we cannot just write out some neat small equation that we can evaluate, but what we'll then need to do is actually take the classic approach for simulations. This is really the fundamental concept that we always need to do. We need to discretize it and integrate it numerically. So discretization here is an important keyword. I will come back to that many times. The equations I had on the previous slide, those are continuous. It's a continuous mathematical description. We'll never really get that in a computer. We always have to boil it down to zeros and ones. That sounds a bit nitpicky here now, but this is really, in a way, a fundamental challenge. We typically cannot just describe and work with smoothly changing numbers, but this is discrete. This is always being updated in certain steps, and in the computer we typically cannot get around that. So this discretization is a crucial step for all of the simulations, and something we typically do beforehand, breaking down some smooth description into discrete sampling points or discrete objects, partial objects. And then once we have that, then we integrate that numerically with numerical methods over time, which typically means, for example, computing a solution over time as an approximation. Right? Not like this analytic form that we have there, but this kind of piecewise process. Yeah, on the slides you can find a few learning outcomes for this chapter, right? Dealing with formal objects and strength systems. We'll look at the physical model. We'll look at these integration methods and also at some implementation aspects. This is what will follow in the next couple of sessions. So with that, now let's come to the actual mass-spring systems. Yeah, as mentioned before, the important start for our procedure is this discretization step. So we first, I'll come to an example in a moment. We need some description we can work with in the computer that basically will be these particles as sampling points. Having these points, we then need a model for the internal forces in the object, and that's going to be the quantity here denoted as Fint, or F internal forces between 2 points ij in our object. And yeah, main point is that we want to distinguish the internal from the external ones. External one would be something like this gravity, which is relatively boring. It's just acting everywhere in the same way, right? As shown in the previous example. That's actually relatively easy to deal with. The internal forces, on the other hand, that depends on the current state, on the deformation and the internal stresses of an object, and this is what we'll be focusing on in a way in the future. One subtle point here is that that nicely comes out of this description, also something we'll get back to later, is that we have a kind of anti-symmetry of these forces, meaning if I go from I to j, get some forces, then that is equal to the negative of the forces from j to I. We'll go into that with a bit more detail later on. The important bit here is that this basically will later on lead to a conservation of momentum, or intuitively what it means is that if we have some object, and imagine you have something like a rubber duck, and you pull it in space and let it go, then from this object itself we will not get any global motions. If you just pull it on the spot in a certain direction and let it go, then it will basically oscillate around its current point, but it will not just start drifting somewhere. For that, we would need something like an external push, but from the internal forces by themselves, the object will not start moving and going somewhere. That those only act around, typically around the center of mass. Yeah, so this is a basic property. Now let's look at this discretization that I've talked about or hinted at before. That's an important aspect now. So let's imagine we have a really simple object, this kind of deformed house-shaped object here on the left. Intentionally, this is a bit abstract now and it could be anything. The goal is now we want to sample this with mass points. And the orange dots here are now an example of such a sampling. Let's assume we know the mass of this object. Mass will be, the whole mass will be denoted by this capital N. And the number of points is typically a lowercase n. So another slightly simplifying assumption that we're going to make is that for each of these sampling points, we'd assume it basically has an nth part of the overall mass, and typically also you could relatively easily experiment in your implementation later on with varying that mass, but you can imagine this is basically just a quantity per mass point and relatively easy to deal with. We'd assume without loss of generality basically that this is a constant. Yeah, so but one of the key challenges now is we want to know these points, they now should describe this object, the blue object, and we want to know how do they move over time. Well, for a simulation, we will not have this blue object, right? So we have these sample points. So you can already see those might not have been the best ones. They only roughly describe the object we're interested in. This is a potential example of a discretization error. So our shape could be more complex with a few select points. It might actually be difficult to really represent the right object or the full object that we had in mind for our real-world setting. But now one nice thing is that Newton's second law works very nicely additively. So if we have all these different force components, we can show that we can quite easily just sum all these forces up, the external ones and potentially a larger number of internal ones that we have, and together, knowing the mass, we bring the mass over again to get an acceleration for one mass point in our object. Here the AI might be the quantity we're interested in. If we bring the m over, then we have the acceleration of 1 point here in our object. So if you now see this equation, the main question, of course, is how do we compute all these internal forces? And this is now, not too surprisingly, where the springs come in. So far we have this collection of points. Now we introduce some springs. For example, the ones I've shown here on the left. Again, this is intentionally a somewhat crude model for the original object we're interested in. But now together, the points and these springs, these should describe this blue box that we were interested in originally. And it's actually also, in a way, a point that is not fully or not easily determined which of these points should be connected with springs. As you'll notice intentionally here, not all of them are connected. So for example, these two are not connected. There might be some modeling choice. Out of the box, it's not always fully clear where to connect these springs. Nearest neighbors are a good starting point, but beyond that, there can be ambiguities. Now, having some springs, we can now move towards computing these internal forces, and there the crucial component is Hooke's law. So I hope some of you actually remember Hooke's law a bit. Informally, we can express that the force experienced by the endpoints of a spring is proportional to the deformation of that spring, meaning to the deviation in length of the spring from its rest or regular length. The springs always assume to start with a certain length, and then if I pull it outwards, we have this force pulling it back, or if I compress it, then that's a restoring force. So key point here is proportional, meaning there's a linear relationship depending on that deviation from the rest distance that gives us a force. There's a few comments are worth noting here. Elasticity typically means we have an object that has a clear initial state that it wants to return to. So I'll move to the side for a moment. A good example is a rubber duck. It has a clear shape. We can squash it, but it will basically just return to its initial state. This is in contrast to plasticity. So crumpling metal is a good example. It also deforms, and in the deformed state it might actually look like rubber, but it will not completely return to its initial state. So I hope you can imagine with such a car crash, this car will not look new after that crash. It will store, basically, as a permanent change of its state, some of the energy from that impact. And the extreme in that direction is now a fluid, which is perfectly plastic. This does not have any memory of an eternal state. So we can basically see different materials as part along this continuum. And now with the mass springs, we're actually dealing with perfectly elastic objects, this end of the spectrum. Later on, we'll have examples here. This middle part, the plasticity, this is a bit more difficult to model. I'll give some pointers, but we'll focus on the two extremes, the elastic part and the perfectly plastic part in the following. For elasticity, how does these Hooke springs look like? Now we can formalize the aforementioned concept a bit more. So for a Hookean spring, we have a spring stiffness, typically denoted by K. Oh, to move a bit again. In addition, we have the initial length, the rest length, if you want, capital L, the current length L, lowercase, and then we have this linear force. So in this setting, it actually looks very easy. So here we have, this is actually the magnitude of the force. So the length of the force vector, that is proportional to be by definition minus, with a minus sign, the stiffness and this deviation of the length. And then you'll see capital L is rest length. So if, for example, if we extend the spring and the current length is longer than the rest length, then this will actually be a positive value, getting a minus sign to go back to the initial state, and by construction the other way, what's shown here, if we compress the spring, then this L will be smaller, we have something negative here, and overall a positive value. And note that with this definition, now it actually acts with opposing signs in with the same magnitude on both ends of the spring. But yeah, in this viewpoint, this now just tells us about the length. We didn't really check in which direction does the spring push. Practice, that's important, of course. So that's the next variant we need to look at. And this looks more complicated on first sight, but I hope this is still quite intuitive. So now with this bold face, we actually denote vector quantities. So you can see here this non-bold, that is a scalar quantity, that's just the length. And the bold, that means it's a vector with a direction, or here also the L, that is just a length. And now to get towards this directed force, we need to look at the actual positions of our mass points. So from ij, as it's defined here, is defined as position of I minus the position of point j, kind of following the order of the points here in this difference. And now it's the difference in position divided by the lowercase l. I hope you remember what the lowercase l was. Lowercase l is the current length of the spring, right? Xi and j are actually the endpoints here. Lowercase l is the length of this. So this whole part actually gives me a normalized vector. This is the direction vector between the 2 points on the spring. And this was the length of the force. This is a normalized direction vector, and hence we multiply it here with the length to get the force in the right direction with the right amount. Yeah, so in practice, of course, we only rarely deal with single springs. In practice, we'll have a larger number of springs. So here's still a pretty simple system, but with 4 mass points now and 3 three springs. And as you can see now, here we would now go in, and for example, looking at the central mass point, we want to compute the internal forces. We need to accumulate the forces acting from all connected springs. In this case, all of these are connected. So in this case, we would need a sum going over all the three springs. And now each of the springs potentially has its own characteristics, of course. So all these uppercase and lowercase length vectors and the stiffnesses have an index for the different springs. And now we basically loop over the connected springs here, compute with respect to x0 all the distances to the other points, 1, 2, 3, evaluate these direction vectors, multiply them with the length of the desired force, and here this is now the minus sign for Hooke's law for all three of them, and we accumulate the forces here. Yeah, and in this setting now, then we have all the internal forces acting on point 0. For a simulation, to get the overall forces, we now also need to take into account the external forces, gravity, for example, if we are dealing with a setting where we have gravity. Or this could also be coming from a user or so, but this would now give us all the forces acting on one of these mass points. So this is, right, now we've made an important step forward. Now we know both the external inferences and the internal ones from an object. This is an important part of our physical model. Yeah, for now, I mostly want to introduce these. So it's actually not yet clear what do we do with the forces, how do we move on. Let me introduce another aspect here, namely damping forces. This is potentially something that plays a role in many practical simulations. And damping typically depends on the motion. So if we have the velocity of a point, we basically assume if it's moving very fast, it experiences a larger damping than if it moves very slow, right? Or if it's not moving at all, right? There is no damping due to its motion, then it would be 0. This is a very simple damping model. We just have this parameter here for the damping, but typically also with a minus sign because it opposes the motion. And this in practice is actually used to model friction effects. So yeah, you can imagine it's a bit like different parts of the material rubbing against each other. This effectively removes energy from the objects I'm interested in. Typically these dissipate into heat, which we don't consider. So essentially these parts are gone. And it is actually something we pretty much always have in reality, and in simulations we might actually also be interested in it for stabilization. If we don't have this, right, energy might not go away, or if we have errors, it might actually increase in undesirable fashions, and this we want to counteract in a way. So the reason I'm introducing this damping is this now depends on the velocity, right? If you think about Hooke's law, this kind of depended on the positions where the points were in order to stretch and compress a spring, and that now gives us a nice formulation. If we now look at this together, we get the following equation, which looks not trivial at first sight, but this is actually still Hooke's law. In a way, this is still very simple, right? Here we have all the forces, and here we have a mass, and well, this is just now a bit of a complicated way of writing the acceleration. Acceleration being the derivative of velocity, which is the derivative of the position, so acceleration is the second derivative. Here we have the velocity component and here we have something that actually depends on the x. Right? So in a way, this is just still Newton's second law. This is the acceleration part. Now, if you look at this part, these are the internal forces I've just described. Typically in our models that we consider now, those are coming from Hooke's law. And these now depend on the position directly. Right? Acceleration second derivative, this is no derivative, zeroth derivative if you want, depending on the position. And then next, here on the right-hand side, we have these damping forces. Those now depend on the velocity, which is the first derivative of the position. So, no coincidence, I'm writing it in this way, right? So now we have different components depending on, right, in a way, no position information at all. Right? This is just purely external. And something depends on position, first derivative, second derivative. So in a way, now we have an equation here that relates different temporal derivatives of our positions with each other. This is a differential equation, but this now describes all these different components and brings them together, what we described so far. This Newton's second law with the internal forces, some external influences, and these damping effects. And this now provides an important physical basis for simulations. These are the equations of motion that we will be using to simulate these mass spring systems. So this is now still a bit if you want, the derivation of the physical model we'll be working with, but this gives us a basis, a basic model that we can now evaluate and compute solutions for. So this is what we will be using in the next couple of sessions to then compute solutions for mass spring systems over time. Yeah, and I think that is a good point to stop for today. Now we have equations of motion for a system, and now next week potentially we'll continue with aspects of how to actually compute solutions for it, and also some aspects of implementation of getting this into the computer. And also next week we will start with the exercises and give you more details about that. So thanks so far. For those, just as a reminder, as mentioned before, for those who do not have a group yet, please think about or get in touch with people who might want to form a group. If unsure, just contact us and we'll put you in touch. See you next week.